வணக்கம். Capacitors. Capacitors are the most widely used passive elements in circuits. Capacitors are the devices which can store electric charge. Capacitors may be used to build up sufficient electric charge to fire. For example, flash tube or laser. They are used in tuned circuits, timing circuits, filters, amplifier circuits, oscillator circuits, and relay circuits. They are also used for power factor correction and for starting single phase motors. The reactance of a capacitor of capacitance at frequency F is given by Xc equal to 1 by 2 pi Fc ohm. The capacitive reactance varies inversely with the frequency of the applied AC voltage. Therefore, the capacitor allows higher frequency current more easily than the lower frequency current. For DC voltages, that is F equal to 0, Xc equal to infinity. Hence, a capacitor blocks the DC voltage or current. A capacitor essentially consists of two conducting plates separated by a dielectric material. The capacitance of parallel capacitor is given by C is equal to epsilon naught into epsilon R into A by D, where A is the area of each plate in meter square. D is the distance between the parallel plates in meter. Epsilon naught is the dielectric constant, that is permittivity of free space, is equal to 1 by 36 pi into 10 power minus 9 farad per meter is equal to 8.854 into 10 power minus 12 F per M. Epsilon R is equal to relative dielectric constant permittivity. For large capacitance, the area A and the value of relative permittivity of the dielectric must be large, while distance must be very small. Large capacitance can be obtained using high permittivity dielectrics of small thickness. When a voltage V is applied across the capacitor plates, the electron accumulate on the side of the capacitor connected to the negative terminal of the voltage source. The plate connected to the positive terminal of the voltage source loses electrons. This accumulation of electrons produces negative charge on one side of the capacitor, while the opposite side has a positive charge. Thus, with the application of voltage, the electrons are simply redistributed from one side of the capacitor to one side of the capacitor to other side of the capacitor. Non-polarized electrolytic capacitor. The basic structure is shown in the figure 2.13. 2.13. Sorry. Actually, இதோட diagram இல்ல. This type has two outside coated anode. For an equal size polarized capacitor, the non-polarized type has one half the capacitance on same voltage rating. They are generally used in applications such as AC motor starting, crossover network, and large pulse signal. Aluminum type. This type of electrolytic capacitor are available in polarized or non-polarized form. The construction of this type of capacitor is similar to the construction of polarized or non-polarized capacitor. This type of capacitor have high DC leakage and low insulation resistance. They are low in cost and have a high volumetric efficiency. The disadvantages are that the shell life is limited and the capacitance deteriorates with time and use. Tantalum type. Tantalum electrolytic capacitors have long shelf life, stable operating characteristic, increased operating temperature range, and greater the volumetric efficiency. The disadvantages of tantalum type in comparison to the aluminum type are its greater cost and lower voltage rating. Tantalum electrolytic capacitors can be divided into three types, namely foil, wet anode, and soil anode. Foil type. The tantalum foil type is similar in construction to aluminum foil electrolytic type. Wet anode type capacitor is made by molding a mixture of tantalum powder and binder into the shape of pellet under the high temperature in a vacuum. The pellet mixture is welded together, and due to the sintering, the binder and impurities are driven off. This result is a porous pellet on which a layer of tantalum oxide is electrochemically formed. The volumetric efficiency of wet anode type is about 3 times that of the foil type. Solid anode type tantalum capacitor is made by sintering an anode pellet on which a layer of tantalum oxide is formed. The pellet is then formed with a manganese dioxide layer which serves as a solid dielectric. The cathode connection is made by coating this pellet by carbon and silver paint. The solid anode construction is most widely used. It has the longest life and lowest leakage current of the three types of tantalum capacitors. Ceramic capacitors uses ceramic dielectric with thin metal films as electrodes bonded to ceramic. There are three basic types of ceramic dielectrics: low permittivity, medium permittivity, and high permittivity types. Low permittivity ceramic capacitors can be made to exhibit zero temperature coefficient, and they find wide use in temperature compensation networks. The permittivity usually ranges from 6 to 400. It operates at voltage as high 6 kilovolt and temperature up to 125 degrees Celsius. Its capacitance value is generally limited to 0.001 microfarad. In the medium permittivity ceramic capacitor, the permittivity is in the range from 500 to about 4000 and is relatively stable over a wide temperature range of 55 to plus 125 degrees Celsius. Its capacitance value is generally limited to 0.001 microfarad. In the medium permittivity ceramic capacitor, the permittivity is in the range from 500 to about 4000 and is relatively stable over a wide temperature range of 55 to plus 125 degrees Celsius with a maximum capacitance change of plus or minus 15%. In the high permittivity ceramic capacitors, the permittivity ranges from 5,000 to 3,000, 5,000 to 30,000. They have capacitance value up to 2.2 microfarad and maximum working voltage of 100 volt. However, these capacitors change their values appreciably with the temperature, DC voltage, and frequency. The medium and high permittivity ceramic capacitors are used for bypass and decoupling the applications or frequency discrimination, where the Q factor and stability are not of major importance. The ceramic capacitors are available as disc, tubular, monolithic, and barrier type capacitors. Disc capacitor. Silver is fixed on both sides of the ceramic to form conductor plates. The sheets are then baked and cut to different sizes of 0.5 millimeter. The terminal leads are attached by pressure contact or soldering. The disc capacitors have high capacitance per unit volume. Round disc types with axial leads are used for high voltage operation. The discs are lacquered or encapsulated in plastic or phenolic molding. They are available up to a value of 0.01 microfarad. They have a voltage rating of up to 750 volt DC. Some disc type capacitors are shown in the figure. Tubular capacitors. The low loss type capacitor are normally made up of stearate or similar material. Stearate has a permittivity of 8. They are usually made in tubular structures. The construction of tubular capacitor is shown in the figure 2.17. The required materials are ground and fixed thoroughly. The mixture is compressed and fixed with suitable fluxes and molded into tubes. Silver metal is deposited outside and inside the tube. Leads are formed and soldered. The outer surface may be protected by lacquer in the insulated types. The tubular capacitors are available in the range of 5 picofarad to 1000 picofarad in voltage ranges up to 5 kilovolt and up to 10,000 picofarad in the lower voltage ranges. Monolithic capacitor. The monolithic capacitors, as shown in the figure 2.18, the monolithic capacitors are formed by interleaving the layers of ceramic and platinum electrodes. The first stage in the manufacturing process is the preparation of slurry or slip in either aqueous or organic solution. Organic binders and plasticizers are added to the slurry to give strength and flexibility to the film. This is then cast on the carrier substrate in thickness of 0.025 mm to 0.75 mm and cut into strips. The next step is to apply screen electrodes of platinum or palladium to the film. The electrode configuration is designed in such a way that each layer of film, when blanked with carrying an electrode, the deposition of metallic layer extends to alternate phases and accurate location of electrode pattern is required. After the required number of layers have been formed for a specific value of capacitance, the stripes are subjected to consolidation under pressure. Then the external electrodes are applied in order to pick up the edges of the internal electrodes and form a parallel connection. This entire structure is fired to form a monolithic block. Sintering is done at high temperature to reduce the volume of the block by 40%. Some monolithic type ceramic capacitors are shown in the figure, shown in the above figure. Some monolithic type ceramic capacitors. Barrier layer capacitor, barium titanate. Barium titanate is used as the dielectric medium in these capacitors. If such a ceramic disc is reduced at 1300 degrees Celsius, it becomes a highly non-conducting medium. If reoxidized, a conducting layer of ceramic forms at the surface. This barrier of conducting to non-conducting layer possesses high values of dielectric constant. Suitable additives will improve the dielectric constant and loss angle. Silver electrodes are fired on this barrier layer and the entire assembly is reoxidized in hot air once again. This is encapsulated to prevent the entrance of moisture. The construction of a barrier type capacitor is shown in the figure. The capacitors have lower insulation resistance and are used only for low voltage application. They have high temperature limitation and can operate from minus 40 degrees Celsius to 80 degrees Celsius. These are used in very high frequency circuit application. Uses of ceramic capacitor. The ceramic capacitor are widely used as a bypass capacitor and in decoupling and biasing application. The major drawback is that the capacitance value varies with the temperature. Ceramic capacitors are of insulated type are used in TV resistors. Tubular capacitors are used to isolate the antennas in receivers. Capacitors with little temperature capacitance variations are used to compensate for impedance temperature changes in circuits. The capacitance uses a plastic film as a dielectric. The plastics used include polystyrene, polycarbonate, polytetrafluoroethylene, and polyester. Plastic capacitors are available in typical ranges of 500 picofarad to 10 microfarad. When sealed properly, these plastics exhibit good mechanical strength, resistance to heat, and chemical inertness. The chief characteristic of the capacitors are their very high insulation resistance, high reliability, small physical size, and low dielectric absorption. Polystyrene capacitor. Polystyrene is a hydrocarbon material and has low permittivity than polyester and polycarbonate. These capacitors are made by rolling the polystyrene film with aluminum foils. These are compactly wound and the leads are soldered at the end. The entire assembly is carefully heat treated so that the plastic softens and makes the good contact with the metal foil. The winding requires particular attention because it may accumulate electrostatic charges and attract dust. Polystyrene is not suitable for metallizing because of lack of available oxygen for self-healing action and low tensile strength. They exhibit a low dissipation factor, small capacitance change with temperature, and a very good stability. They tend to be large in size, and the maximum operating temperature is 85 degrees Celsius. Polystyrene capacitors are normally used in coupling, resonant, and measuring circuit. As these capacitors have low dissipation factor, they can be used for AC applications. Polyester capacitor. Polyester capacitor. These are made up of polyester like mylar, Melinex, Terilene, etc. Usually, this is metallized to give better result. Sometimes, impregnation is done with silicon or mineral oil to improve the dielectric characteristic. A thin film of silver is deposited on the plastic by vacuum evaporation. The capacitors are capable of withstanding temperatures up to 150 degrees Celsius and voltages up to 400 volt. The capacitors are available in the range from 100 picofarad to 2 microfarad. As a dielectric is prone to moisture, good encasement is needed. The capacitors are usually encased within a glass or resin molded or ceramic capacitor. Polyester is a tough polymer with a high tensile strength, free from pinholes and with good insulating properties over a reasonably wide temperature range. Its combination of good insulation properties over a wide temperature range and a high mechanical strength are the outstanding characteristic. It has a it also has a low moisture absorption. The high mechanical strength make polyester ideally suited for metallizing by vacuum evaporation. It consists of sufficient oxygen to produce good self-healing due to good all-around mechanical and electrical properties and high dielectric constant of polyester film. These capacitors are the most widely used of any film or paper capacitors. Polyester capacitors are normally used for coupling, decoupling applications at low and medium frequencies, but find many other applications in general and in power electronics, as well as in certain AC applications. Polyester is ideal for DC application because of its high dielectric strength and resistivity. Polycarbonate resistors. Polycarbonate is a polyester of carbonic acid bisphenol. It combines good physical properties with lower dissipation factor than polyester. The metallized polycarbonate film is rolled and sealed in a metal case with epoxy resin. It is insulated with a polyester sleeve as it does not have much available oxygen. Its self-healing properties are not as quite as good as for polyester. It has high insulation resistance.